Hi, Jenny. Sometimes I just wonder how much energy we use just to control the room temperature. In hot places, we use air conditioners, and in cold places, we use heaters. It's like we're constantly burning energy to maintain comfort.
True. It's crazy how much power goes into heating and cooling our spaces. But what if I tell you, in the future, we might be able to reverse the process and use room temperature to produce energy?
How is that even possible? We're always using energy to change the temperature, not the other way around.
Have you heard about thermoelectric devices? They can actually convert heat into electricity.
I know about those. That's how space probes like the Mars Curiosity rover and the Voyager spacecraft stay powered for years, right? Thermoelectric devices generate electricity through something called the Seebeck effect. These devices rely on a temperature gradient. One side of the thermoelectric device is hot and the other side is cold. The Mars Curiosity rover used the heat from radioactive decay as their heat source, and space acts as the cold side.
Exactly. The Seebeck effect is the core principle. When you have different temperatures on two sides of a thermoelectric material, electrons move from the hot side to the cold side, creating a voltage. It's pretty amazing that this same principle powers space exploration, especially in places where traditional solar panels wouldn't work due to low sunlight.
I thought thermoelectric devices only worked in extreme conditions, like the big temperature differences in space. Could this ever be useful on Earth, where the temperature difference between indoors and outdoors is usually not that dramatic?
That's the challenge, right? Traditional thermoelectric devices need significant temperature gradients to generate meaningful electricity. But here's the exciting part. Researchers from Kyushu University in Japan and their partners are developing an organic thermoelectric device that could work at room temperature, even without needing a large temperature difference.
What? Organic materials? Wait, how does the organic material work?
Yes, Ryan, organic materials. The researchers combined the charge separation ability at organic donor-acceptor interfaces with the diffusion ability of organic semiconductor layers. Basically, they're creating a new mechanism for thermoelectric power generation that can harness low-level thermal energy. This means we could potentially generate electricity from just the heat in a room, without needing a drastic temperature difference.
So they figured out a way to harvest energy from heat even at room temperature? That's incredible. They're using existing knowledge about charge interactions in organic materials to make this work. If they can perfect this, could we really power things like phones or laptops just from room temperature?
That's the dream. We're not there yet, but it's a huge step. Right now, the energy they can produce is extremely tiny, just in the range of microvolts or millielectron volts, so it's still a proof of concept. But if they can scale it up, it could be revolutionary.
Imagine powering wearable devices or sensors just from the ambient heat in the room. That really makes me excited for the future. I had no idea organic materials could be so versatile.
The key challenge now is increasing the efficiency of these devices and finding ways to mass produce them affordably.